this was us in January 2017. We were literally getting crushed under the weight of our MySQL database. We were running out of disk space. We could barely get through a day's worth of transactional volume. And Netflix just kept adding more members. We had no idea what to do. We were running out of ideas. We faced a very uncertain future. And this is us in July 2018. Our application is now running on Cassandra. We have horizontal scalability. We have fault tolerance. We have performance. And we are firmly in control of our future. I'm Rahul Pilani. I'm going to talk about building financial systems on eventually consistent databases. This is mostly about our journey from MySQL to Cassandra. But a lot of the things that we did, you can learn and apply to other eventually consistent databases as well, which are similar in characteristics. Practically everyone knows Netflix, but we're an online video streaming provider. We have 130 million customers worldwide, practically in every country, except China and Korea. My team, billing engineering, we do subscription billing for Netflix. We figure out who to charge and when to charge. So if you're supposed to be charged on the 5th of the month, our team's job is to make sure that it's the 5th, not the 4th, not the 6th, it's the 5th. We also do financial reporting. So what that means is, given that we charged, say, 4 million customers yesterday, we roll that up in a report, aggregate it, and send it over to our financial guys, who eventually report it to Wall Street. So we're like a SOC system and stuff like that. We also manage gift cards and balances. So if you apply a gift card to your account, my team is the one that manages that state. As you can imagine, to do all of this, we rely on many microservices. Some of them are offline, like the subscription billing part that figures out who to charge. That can take a downtime. But the ones that report the state of the customer to our upstream services, whether they've paid or not, and consequently whether they can be charged or not, those have to be online, and not only just online, they have to be fault tolerant. Now, you might think that it's billing. Why does billing to be available? As long as I can stream, who cares of whether I paid or not? Consider this scenario. You report your credit card stolen. So Netflix can no longer charge you. And it's Friday night. You want to catch up on your favorite new show, but we've stopped your streaming. And so you say, no problem, I'll update my credit card, and I can start streaming again. So you go online, you try to update your credit card, and you see something like this. In this moment, at this point, we've failed you. We've come between you and your favorite piece of content. We never want to be in this position. We never want to be the reason why you can't stream Netflix. Netflix has also grown crazy for the past 10 years. We've grown more than 10x. And when we set out to build our new system on Cassandra, we looked at this and we knew that whatever new system we built had to be scalable, had to grow with how Netflix is growing. Netflix as a whole operates in multiple regions for availability reasons. If we detect a problem in one of the regions, we seamlessly shift traffic from one region to another, and our members don't even notice. And the problems can be different, right? Like it could be, we did a deployment, and suddenly stuff's breaking. No problem, we shift. It could even, more recently, you had a case where Hurricane Florence was hitting US East 1, and we shifted traffic, and no one was affected. We wanted to be multi-region available like the rest of Netflix, but we were on MySQL, and MySQL is decidedly single master. There are other options like Aurora, but they're multi-AZ, but not multi-region. Being on MySQL and a single master database means you also have a single point of failure. Now, there are ways to kind of deal with it. A couple of them is using read replicas and having a warm standby to fail over to. And there were still problems with those. consider this kind of topology where we have read replicas in other regions, and we do a read-write in one region. What we saw in practice was if there was a heavy load on the master or some networking issues between the regions, you could get stale reads. And now we're serving stale state to our customers, so they apply a gift card and they're suddenly not seeing on their website, and you get a lot of CS calls. The other strategy of using slave promotion. So imagine the scenario where you have a master and 3 slaves. You promote the slave that's in your local region, and now you've lost all of your other slaves. And you have to rebuild those slaves from scratch. With our case, we had like terabytes of data, and rebuilding that would take days. And in that time, with one master and no slaves, we were vulnerable. We couldn't survive another failure in that time. So we wanted to get rid of this situation as well. We needed something better. We wanted something that was fault tolerant, something that could grow with how Netflix was growing. We needed something that allowed us to switch regions. And if there was a failure, we could recover quickly. Cassandra fit the bill. It was horizontally scalable, it's multi-master, and it's fault tolerant. There were other benefits for using Cassandra. Cassandra is widely deployed at Netflix, so we have a lot of experience to fall back on. Cassandra is also well integrated into our big data system, so we could use those tools. We have an internal team that manages, deploys, patches Cassandra, so we could rely on them for DevOps, because if you want to use your own database at Netflix, you have to do your own DevOps. And finally, the thing that allowed us to use Cassandra was the support for atomic compare and set that had just matured. But it's not perfect, especially not for a financial system. It's eventually consistent. It lacks transactions, so you can not roll. There's no rollback. You have to manage your rollback yourself. It's not relational. So coming from a traditional database system where we had relations, this was kind of a mismatch. And finally, one of the main things that we did was financial reporting. And financial reporting or aggregate reporting is simply not supported on Cassandra. And definitely, it's kind of supported, but it's definitely not recommended. So how do you build something that's a financial system on Cassandra? Well, so for eventually consistent and lack of transactions, we use the atomic compare and set primitives, lightweight transactions. For not having relational schema, we wrote our entire relation in one row. Finally, for not having aggregate querying abilities, we simply replicated our writes to another data store. And we did our OLAP queries and aggregate queries from there. Let's dive into these a little bit more. Consistency. Lightweight transactions. What are lightweight transactions? They are not transactions. They're completely misnamed. They're actually atomic compare and set primitives. What does that mean? So if you do an insert, you can say, only let that insert succeed if that ID does not exist. So you can say, if not exists. And if you do an update, you can say, only let that update succeed if a volume, a particular column is a particular value. So you can say, update if x equals y. It's available since Cassandra 2.0. And the way they're implemented is Cassandra implemented its own version of Paxos on top of it, which actually took 4 different round trips to complete one write to the database. Let's look at how we implemented updates. So the way we did the updates was using optimistic locking. Consider a schema like this, where you have an ID column, a name, and a version column. The first thing you do is you select from the row that you want to write to. And so you select star from widgets where ID equals 1. And now you note the version that row is in the database. Currently, it says version 1. Next, you issue the update. You say, update widgets, set name equal to bar, increment the version to 2, where ID is equal to 1, only if the version in the database is what I read just a second ago. And so there are two scenarios that can happen. The update succeeds because the version in the database was 1, and you were successfully able to override it with 2. And the second one is the update fails because someone overrode that row while you were processing it, and so you get an applied equal to false, and you have to retry. Actually, I lied. There's a third scenario. Your update can succeed in your region, and another update can succeed in another region, and now you're kind of screwed. With Cassandra, last write wins. And so if one region contains one write and the other region contains the other, they will eventually reconcile. And which one will win? Based on timestamp. If bar was written first, bar is the one that will override everything. Baz was written first, Baz will override everything. Why does this happen? Well, it's happened because of a design choice that we made. We chose to use local quorum as our consistency level. And local quorum ensures atomicity only within a region. So if you have cross-region writes to the same key at the same time, you're kind of on your own. Why did we use local quorum? Why did we want to get into this kind of situation? To see that, let's step back a little bit and see how Cassandra does fault tolerance. The way Cassandra does fault tolerance is by replicating writes. And it's called the replication factor. You can say, replicate my writes to 3 different nodes so that if one node goes down, I can rely on the other 2. Of the 3 nodes that you write to, the write should succeed on a quorum of nodes. That's the majority of the nodes. So this is an example. The diagram shows a local quorum in which the write is going to 3 nodes, but it's relying only on an act from 2 of them, and the client was given the success. There are various levels that you can configure Cassandra to. I'm going to talk about local quorum and each quorum, which is the global consistency level. And each quorum means Cassandra will expect a quorum of nodes to acknowledge the writes in every region. And so you can see that it's fanning out to every region for every write. Now, I mentioned that Cassandra uses its own version of Paxos, which has 4 different round trips. In this scenario, now you've blown up your round trips to 12, essentially, instead of 4, if you have 3 regions. And so Paxos across regions is really expensive. Your average case will be 12x. Your 99th percentile will be crazy because some node somewhere is failing. So in order to keep latencies low, we chose local quorum. But it's a trade-off. We gave up global consistency for latency. Let's jump back to inserts. How does insert work? Well, we cannot use optimistic locking because there's no row in the database yet to check the version of. But you can still use the atomic compare and set primitives. You can say if not exists. But in order to have that, you need to know the ID beforehand. What we do is, for a given payload that we need to write to the database, we figure out an invariant. We say, in our case, what it meant was a member was supposed to be charged only once for a given month. So we used that as an invariant and said, there should not be any other row for the same month in the database. And so we took those data columns, we hashed them up using UUID v5, and we generated a key using that. And we used that as an invariant. The reason why we needed this was mainly because we used SQS for delivering those payloads to our application. And SQS guarantees at least once delivery. And so you can get this into the situation where you have duplicate delivery and you have to counteract that. But this doesn't prevent something like a double click or those kind of scenarios. So this is an example of that. If you have a system like a shopping cart system, you can hash the product code values, the cart ID that was used at the time, into a single UUID v5 and get that. And as I was mentioning, like it wouldn't protect against like a double-click scenario in this case. So with this scheme, there are some things to consider. Even though Cassandra is really fast at writing, it's built for writing. Lighter transactions will make that at least 4 times slower. And you have to do that read before writing anyways. So all of those will add up. So if you need the raw write capabilities, this will definitely slow you down. When those 4 round trips are going on, it could happen that the coordinator node fails on the final step. So all of the nodes have acknowledged the write. The write has actually succeeded, but you get a failure. So you have to keep in mind that. Each quorum is really expensive. And if you use local quorum, you can get clobbering writes. So you have to deal with that as well. And finally, we could use inserts and the scheme of using invariants because we had an invariant. So your system needs some kind of invariant to generate those IDs. So that's what we did. To handle coordinator write timeouts, we actually, if we get a write timeout, we check again, we read again, and check if the row actually exists in the form that we want in the database. And only if it doesn't exist, we throw that failure back to the client. If you get an atomic write failure, like an applied equal to false, you simply throw it back, and you have to retry the transaction from the start, and do all the invariant checks that your system needs. You have to ensure that a write to a given key is happening only in one region at a given point of time. Of course, it can happen across regions at different points of time. The way we ran into this when we first built the system. And so the way we solved it, what we were doing earlier was that we were writing in one region, and then we were writing to SQS, and then processing that write in another region. And that was the thing. So it's not just a customer doing an interaction, the same interaction in different regions. It was we who were interacting with that row while the customer was interacting in another region. And so to prevent that, what we did, we moved all of the processing in the region that the write originated in. And that solved a lot of that issue for us. And finally, you have to generate an ID based on those invariants so that you can prevent things like duplicate insertion on SQS delivery. If you're still paranoid, which we were, you can still do more. What we did was on every write, we would replicate that write to Kafka. And every night, we would take a snapshot of Cassandra and upload it to Hive. And then we would compare those write events to that snapshot and see if they agree or not. And we did catch a lot of inconsistencies and fixed a lot of bugs using this, where we would see a write being a different state than what the snapshot told us was. Not having a relational schema. Now, we were building a system that was coming from MySQL, so a lot of our data model was relational. We had an invoice. We had a customer who had many invoices and who have many line items on an invoice. And modeling that as a key value structure and flattening it out would have made programming on the application harder. So we didn't want to get that. There was another constraint. If you want to use atomic compare and set primitives in Cassandra, it doesn't allow multi-column family writes. So you couldn't have relations in different column families and have like a single transaction wrapping that. Even multi-row atomic writes are not recommended by Cassandra because simply they're more expensive. Now, more nodes need to be engaged in a single write. So what did we do? We built a poor man's relational schema on top of Cassandra. We took our entire object tree and we flattened out. The top level object was flattened out into columns in Cassandra, but the child relations were serialized to JSON and stored as strings in the column. So if you had invoice and invoice items was just a JSON blob inside the invoice column family. It's very important to understand the characteristics of your database and the different data types that it provides. Cassandra has this helpful data type called collection data types. It has sets, maps, lists. And initially, we were using that. But we found out that the way it stores it is it stores each value as an individual column inside the collection. So it blows it out. And so in practice, reading and writing those are expensive. So what we reverted back to was, if we have a one-to-many relation, we just serialize that as a JSON array and store it as a single JSON blob in the top-level column family. Now, you might look at this and say, this looks a little clunky. It doesn't fit Cassandra perfectly. And you're right, it does. But you lose the ability to do CRUD operations on individual child relation properties. And there's no schema enforcement on your child relations. But there are some good things as well. It's simpler. It works really well with Cassandra's data stacks driver. And since we were reading and writing the entire row at a single point of time, we get this great audit ability, which allowed us to catch inconsistencies. Having no schema also means that your child relations are now flexible. You can do the schema enforcement at read time. Finally, because we did our own DevOps, having fewer column families meant fewer column families to maintain, and it was great for us. Finally, aggregate querying. We needed to build financial reports every night. We needed to build these aggregate queries where we wanted to tell our financial team what happened in the previous day. And Cassandra doesn't support aggregate querying, basically. So what we did, I talked about that Hive snapshot we took every night. We used that instead. And we ran Spark queries on top of Hive and generated reports from that. Now, not everyone has a Hive data lake available, but you can use the same scheme. You can write. Every time you have a write, you can write to another database and do your aggregate queries from there. And we were actually doing that too. We were replicating writes to Aurora for real-time querying as well. So you can use something similar to that. So to recap, you can use lightweight transactions to have consistency. To get that consistency, you can use local quorum mode, but local quorum mode will clobber your writes. For inserts, you need to have some sort of idea of what your ID is going to be to do an if not exists. For updates, you can use a version column to do optimistic locking. And remember that you have to retry on any kind of failure. And we dealt with coordinated writes slightly differently from coordinated write timeouts slightly differently than atomic write failures. Not having a relational schema, we read and wrote an entire row flattened our schema into an entire row and wrote that. Finally, aggregate queries are better done elsewhere. It was a big journey. It was a long journey for us to get here. We migrated our system from MySQL to Cassandra and got massive scalability in return. But we had to design our application considering all the trade-offs. And then once we've engineered the application, we built monitoring on top of it so that we could catch the remaining sort of set of problems. We started building the system early 2017, and it was deployed to production in a very limited form in October 2017. By July 2018, 99% of our traffic started running on it. We got great performance. We were processing 2 times the volume in about half the time. We're now available in all regions. And so we achieved our goal of multi-region availability. We can write to all regions, and we can scale with Netflix. When we began this project, we weren't really sure. Even internally at Netflix, a lot of people were skeptical of us building our system on Cassandra. Everyone was like, really? You're building billing on Cassandra? So there was a lot of skepticism. Hopefully, I've inspired you to not only see that it's possible, but it's a reality. We've done it. So thank you.